Okay, so this particular lecture is going to cover your biochem packet. So you should have your packet that says biochem introduction at the top. And however you decide to take notes, that is completely up to you. You can take notes directly on the packet, or you also can have a separate sheet, take your notes there. Just make sure that however you decide to do your note taking, that they do come with you back to our next class when we meet face to face. So first conversation we had was just an introduction into anatomy and physiology, a little bit of background information. And it's not uncommon in anatomy and phys classes, or even some of your more general life science classes, that very early on you will also cover some chemistry. And the reason for that is, especially when you're looking at the human body, to fully understand how it works, you also have to have some introduction to chemistry principles and concepts so that you can really get a good idea of how things function within the body itself. So if you look at that slide, it talks about body functions depend on cellular functions. And even more than that, taking it back to the atomic level. So when you guys notice things within your body, you usually see the end result. But there were a lot of things that had to happen before to get to that end result. So if you have noticed that your heart rate elevates, in order for your heart rate to increase, there had to be a lot of other things that happened prior to that to get the elevated heart rate. And that is going to happen at the cellular and even the atomic level in order to get that end result that you guys see on the outside. So that's a lot of what our conversation is going to kind of evolve around, is exactly what's going on so that you see that big change or that big result at the end. So if you look at slide number 2, it talks about the structure of matter, and just kind of getting some of those basic chem terms into the conversation. When you talk about matter, matter in its most basic definition is anything that takes up space and has mass. So if it meets those two requirements, you are going to refer to it as matter. And if you've ever seen a periodic table or really looked at it, you know that spread across that periodic table are the elements that we have. And getting an understanding or knowing, being familiar with those elements is important also to anatomy, just because a lot of those elements are going to play a very important role in our body. We have to store some of those things in our body so that we have them on hand to use. A lot of them are used as building blocks to make the different tissues and other structures that we have within our bodies. So elements are going to be broken down into two categories. They're either going to be what we call bulk elements, or they are going to be trace elements. Bulk elements are going to be those that we need in larger amounts. In order to function, in order to make all the things that we need to make, we need to have a lot of that particular element on hand. So we refer to it as bulk. There are other elements that we need, but we need them on a much smaller scale. And so in that category, it would be referred to as a trace element. So within anatomy, it's either going to be a bulk, we need a lot of it, or it's going to be trace, we need it, but we don't need a huge amount of it. And then the very last piece that you have on there refers to the atom. So in every branch of science, you are going to have the most basic form or the most basic unit of that particular branch of science. In life science or anatomy, it is the cell. That is the most basic unit of life. In chemistry, the most basic unit that you have would be the atom. And we're going to talk a little bit more about what that atom actually looks like. So atoms are something that are smaller than a cell, and you can't see them with the naked eye. And most cells we can't see with the naked eye. So if you take something even smaller, obviously it makes sense. Definitely can't see that. So for some people to kind of grasp exactly what an atom looks like or how it works is kind of difficult, because a lot of people, they are very visual in their learning. So on this particular slide, you have a very basic breakdown of what an atom would look like. This is actually a lithium atom, and it is number 3 on the periodic table. And when we look at our atoms, they have 3 basic subatomic parts. They have the protons, they have the neutrons, and they have the electrons. So protons are going to carry a positive charge with them. You can see the plus signs. That indicates where your protons are. And your neutrons are going to have no charge. And so you see the zeros. It's also not uncommon for the neutrons to have an equal sign. And either one is perfectly fine. But a zero or an equal sign, because they don't carry a charge, is going to indicate that you are looking at a neutron. And then the last one that you have is the electron. And the electrons are going to carry a negative charge with them. And you can see those electrons that are on the outskirts of that particular atom. So your atom has a basic form. It does have a nucleus, and the nucleus is going to be right at the core or the center of the atom. Now, two of the three particles of an atom are going to be housed or located inside that nucleus, and those are the protons and the neutrons. Around the nucleus, in that space, you are going to have the electrons. Now, the space where the electrons are located, you tend to get multiple names for them, and depending on the teacher that you had for chemistry, will determine what name you've heard quite a bit. So some places will call it a shell, some places will refer to it as an orbital, and some places will refer to it as the electron cloud. All of them are perfectly acceptable. Whichever one you like best or are more familiar with, you can go with, even if it's not the term that I use. So, and I tend to mix it up just because I have people coming from a lot of different chemistry backgrounds and they might have heard it different ways. So orbital, shell, or electron cloud, all of those are perfectly acceptable to define the space where the electrons are. So if you look at this, thinking about charges and what you know about charges, one of the most basic principles says that opposites are going to attract. So if you think about the design of the atom, you have this positive core. This nucleus is going to give off a positive attraction because it holds all of the protons, which have a positive charge. The neutrons don't carry a charge, and so they're not going to interfere. So you have this mass at the center of the atom giving off these positive vibes, and the electrons are then going to be drawn to that. So you'll notice the 3 protons, and then you've got those 3 electrons. Now, one thing that you kind of have to envision with your atoms is that even in a picture, obviously those electrons are in a fixed location. And that's not truly the case. If this were an actual atom, those electrons are not going to be stuck somewhere. They are not physically attached to a ring. Those don't exist. We create those so that it kind of helps us visualize the atom itself. The best example I can give you as to how those electrons behave around that nucleus is to kind of think of a light that's on at night, and you have all these bugs that are kind of swarming it, and the bugs will get close to the light and then they kind of drift away and they'll come back. And they always kind of stay right in the proximity of the light. That's exactly how those electrons will behave. So they'll kind of come a little closer to the nucleus and then they'll float away. They always stay in the general area, okay? But they are not in a fixed spot. So with that entire setup, just understanding that the protons are going to be at the core with the neutrons and the electrons are going to be hanging out around the outside edge. The next slide that you have covers molecules and compounds. And there are a lot of terms in science, and especially in anatomy, where people use them in place of each other. And it's kind of accepted, but it's not always correct. So when you talk about molecules and compounds, molecules are defined as particles that are going to be created when 2 or more atoms chemically combine. A compound, on the other hand, is a particle that's formed when 2 or more atoms of different elements chemically combine. And this is kind of where the separation doesn't always happen. If you have 2 atoms that have come together, people will call it a molecule or they will call it a compound. The difference is a molecule is a term that you should only use when it is 2 of the same atoms from the same element that have combined together. So if you have 2 oxygen that come together and bond chemically, that would be an example of a molecule. If you have 2 hydrogens, that would be a molecule because they're the same. A compound is going to be H2O. So you have hydrogen and you have oxygen that have combined together. So that would be a compound. Now, compounds are always going to be molecules. Molecules are not always compounds. You will hear those terms used in place of each other. Most people will say a water molecule, and it's H2O. So technically you shouldn't refer to that as a molecule, but it's common practice. But please understand there is a distinction between what a molecule is and what a compound. In order to be a compound, it has to be different elements that are coming together. And then the last piece that you have on there talks about molecular formulas. And so you're just taking the element name and you're showing the element itself and the number of that particular element that you have involved in the compound or in the molecule. So H2 indicates that you have 2 hydrogen, C6H12O6, we have 6 carbon, 12 hydrogen, 6 oxygen. And then you have H2O, so you see the 2 hydrogen. The O has nothing behind it, so if there is not a number present, that is understood as 1. The next slide is a visual to the one prior. So if you look at that, it's just giving you a visual representation of what a molecule is. That's on your left-hand side. And then it's giving you a visual representation of what a compound is. So you'll notice on the molecule side, you have the 2 H's, you have the 2 oxygens, but it is the same type of atom or the same element that is bonding together. On the flip side, now we have 2 different types of atoms coming together, 2 different elements involved, and so now that would fall into the compound. The next slide that you have talks about isotopes, and isotopes are going to be a situation where when you look at atoms, in a perfect world, the number of protons that you have equals the number of neutrons equals the number of electrons. You'll notice I said in a perfect world. So if we were to draw an atom and it was number 2 on the periodic table, the atomic number from the periodic table is going to tell you how many protons that particular element has. So the atomic number is representative of the number of protons that are present in a particular atom or element. If the number of protons changes, the element changes. So you have number 1 on the periodic table, that is hydrogen, 1 proton. If you go up to 6 protons, now you are carbon. So if the number of protons changes, the element that you are talking about changes also. So in most atoms, if you know the number of protons, you know the number of neutrons, and you also know the number of electrons. So within that nucleus, if you have 6 protons, you would also have 6 neutrons, and they would all be housed in that nucleus together. Then you would have 6 electrons floating around the outside of that nucleus. There are always exceptions to the rule because we know we don't live in a perfect world. Perfect world, they're all equal to each other. Doesn't always happen. So, in the case of an isotope is a situation where the number of protons and the number of neutrons are not equal to each other. So you might have 4 protons in the nucleus. Perfect world, you would have 4 neutrons. But there are situations where instead of having the same number of neutrons, you might have 5 neutrons. You might have 3 neutrons. Could be higher, could be lower, but if the number of neutrons does not match the number of protons, that is what we refer to as an isotope. Now, the reason that isotopes are important is because isotopes do something very unique. If the number of protons and the number of neutrons equal each other, that atom is going to be stable. At least the nucleus is going to be stable. And everything just stays kind of put where it's supposed to be. If you get a situation where the number of protons and the number of neutrons do not match each other, in that nucleus, you get something that will happen that doesn't happen in other atoms. The protons and the neutrons will actually break apart, and then they will come back together. Some time will pass, they break apart, they come back together. Time passes and it will keep doing that. So the amount of time that passes in between the breaking and the coming back together is always the same. Could be 20 seconds, could be 20 years, depends on the element that you're dealing with. But every so often, those protons and those neutrons are going to come apart and they'll eventually come back together. But what happens is anytime that you break something apart, you are going to give off energy. It takes energy to hold a bond together. So those protons and those neutrons all bonded together in that nucleus, it takes energy to hold that together. When they break apart, some of that energy is released. And that is what we call radiation. So when you talk about things being radioactive, what you automatically know is you're dealing with an isotope. And you know that those protons and those neutrons are breaking apart every so often, giving off that surge of energy in the form of radiation. Now, it can be very low levels of radiation. There are some rocks out there that you could pick up off the ground that are giving off very low levels of radiation. And there can be also very, very intense levels that would cause damage to tissue and body parts and things like that. So, understanding that isotopes work a little bit different, the number of protons, number of neutrons do not equal each other. Because of that, the nucleus is unstable, the parts break apart from each other, and every time that that happens, that energy is going to be released in a surge, which is radiation. The next slide that you have talks about the bonding of atoms. And so earlier on in the conversation, I showed you that picture of an atom. And I talked very briefly about the electron cloud, so the location where you find the electrons. So for our purposes, we're only going to be worried about the first shell and the second shell. Even though they're a figment of our imagination and they don't really exist, they still tell you something about the electrons. In that first region around the nucleus, you can have a max of 2 electrons that can be held in that region. Just beyond that, it's going to bump up a little bit. That next space or that next region around the nucleus can hold up to 8 electrons. I know it gives you a third one. I'm not worried about the third one. All I need you to know for our purposes is that in that first shell around the nucleus, you can hold a max of 2 electrons. The next shell or space beyond that can hold up to 8 electrons. Now, if you think about those shells, an atom is happy when its outermost shell is completely full. It wants its outermost shell to be completely filled. So if you think about hydrogen, hydrogen is number 1 on the periodic table. It's going to have 1 proton, 1 neutron, 1 electron. So we already talked about where the protons and the neutrons go. They're going to be housed in the nucleus. That electron is going to be floating around in that cloud around the nucleus. Now, that cloud can hold 2 electrons, but hydrogen only has 1. So hydrogen is not happy because that shell, which can hold a max of 2 electrons, is not full. Hydrogen is going to actively work to fill its outermost shell. It wants to get it up to 2. And once it gets it to 2 and that shell is full, hydrogen is happy. So when you think about chemistry, we know that chemical reactions take place. You can put some elements in proximity to each other. You can pour some things in a beaker together, nothing happens. And you can take 2 separate things, put them in a beaker together, and you've got boiling and bubbling and explosions and all sorts of things taking place. The reason for the difference is because you need to understand what's going on in that outer shell. If an atom is looking and needs to fill its outer shell to be complete, it will bond with other elements in order to fill that shell. Or it will give up some of its electrons. It can also kick them out to get that outer shell filled or balanced. So that explains reactivity and why some things react very quickly and heavily and other things don't. If its outer shell is already full, it's stable. It's not looking for anything, and so it's not going to react with other atoms or elements that it comes in contact with. So one of the things that we will do in class is we will do a little bit of work with drawing atoms and then getting a little bit better understanding of how those electrons are going to be shifted and moved around. But that's something that we need to do face to face. So the next slide that you have shows a little bit of that bonding that's taking place. I gave you the example of hydrogen. You can see the one proton, the one electron, and then you have helium right next to it. We have two protons, two neutrons, and two electrons. Now, helium is what we call stable because just by chance, it has two electrons right from the get-go, just because of its makeup. Two protons, two neutrons, two electrons. It is stable. It is not going to look for anybody else to bond with in order to try and get its outer shell completely full. Then if you look at lithium, lithium is number 3, has 3 protons. This would also be an example of an isotope. You'll notice that there are 4 neutrons hanging out in the nucleus. So the number of protons and the number of neutrons do not match. So right off the bat, we've got an isotope there. But then if you go and you look at the electrons, we see that that first shell has 2 electrons. It's full, but lithium is 3 on the periodic table. So 3 protons, you've got your neutrons, and then 3 electrons. So that first shell was filled with those 2 electrons. The third one now bumps to the next shell. We've got 1 electron in that second shell. Go back to your notes. How many electrons can be held in that second orbital or that second shell? That second one can hold a max of 8 electrons. So lithium has to make a choice. It's not happy right now because that outer shell is nowhere close to being filled. It needs 7 more electrons in order to fill that shell and be happy. Now, atoms are going to work very much like people. People will take the path of least resistance. So lithium has to look at this situation and decide, is it going to be easier for me to pick up 7 electrons, to go out and find 7 electrons, grab onto them, and put them in this outer shell, or is it going to be easier for lithium to kick out that 1 electron? It's going to be a heck of a lot easier to kick out that 1 electron. So if you think about what happens then, lithium gets rid of that electron, kicks it out. That shell is no longer there. So now we've got 3 protons in the nucleus, and we only have 2 electrons in that shell. So you've got 3 positive charges, you've only got 2 negative charges. So one of the positives and one of the negatives will cancel each other out. Second proton and the second electron will cancel each other out. But now you have this extra proton that is in the nucleus, and there is no electron any longer to cancel it. So because of that, because you have an extra positive charge in the nucleus, and there is no longer an electron to cancel it out, lithium is going to have or carry a positive overall charge. So when you see an atom and it has a little plus sign behind the name, that's what it's telling you, is that it has an extra positive charge. It gave up an electron, lost one of its negatives, and so now it gives off an overall positive charge. If you see a +2, that means it has 2 more positive charges compared to the negative charges. It can go the other way. It could be a negative. So you might see a -1. That means it has more negative charges than positives. And like I said, we'll go through this next time that we have a face-to-face class. So there are 2 major types of bonds that we will talk about. And one is what I just kind of explained with the lithium. So you can have what is called an ionic bond. Now, if we go back to the word ion, I-O-N, in chemistry, ion means an atom that carries a charge. So ion itself just simply means that you have an atom and it's going to carry either a positive charge to it or a negative charge to it. If you want to get more specific, you have what are called cations and anions. So ion is just a general term, tells you that there's a charge of some sort. A cation is going to tell you that it is an atom that carries a positive charge. An anion is going to mean specifically that it carries a negative charge. So general, ion, specific, cation is going to indicate positive, anion is going to indicate negative charge. So the most important thing to understand or remember with your ionic bonds is that we call them an ionic bond because that particular atom is going to kick out or gain electrons. So the positive charges, the number of protons and the number of electrons no longer match. And because they no longer match, you're going to get a charge of some sort. I'm going to have you skip over to and find the slide that talks about covalent bonds. Covalent bonds are a little bit different. You don't have an atom that is completely getting rid of an electron or gaining an electron. In the case of covalent bonds, you have two atoms that are going to share their electrons. So they're not kicking them out, getting rid of them, but two atoms are now going to come together. They are going to share the use of that electron. Both of them are going to get to fill their outer shell because of that sharing, and that is referred to as a covalent bond. So if you look at the side there, you have some lines or dashes between the element symbols. So you have the H's with the dash between them. You have the two O's with two dashes. You have the N's with 3 between them. What that indicates is the number of bonds that are taking place. So hydrogen would indicate single, the 2 would indicate a double bond, the 3 would indicate a triple bond. So that is the distinction between the number of dashes that you have between those element signs. The next slide that we have talks about polar molecules. Polar molecules are interesting because they behave very differently compared to other bond types. So typically when you have an atom and it is bonding with others, it will, if it bonds with two other atoms, you will have your central atom, and then one atom will bond on one side, and the other one will bond on the complete opposite side. So as it is forming bonds with other atoms, they want to be as far apart from each other as they possibly can be. So they would be on opposite sides from each other. In the case of polar bonds, it doesn't happen that way. So the atoms that are bonding to it, or the molecules that are bonding together, you'll notice in this picture you have the larger molecule, which is actually the oxygen, and then you have the two hydrogens, and you can see where the hydrogens actually are on the same side of that oxygen molecule. Now, the reason that this is so interesting is that it creates a situation where you are going to have one side that behaves positively and the other side is going to behave negatively. So you actually have the situation where it is going to act like a magnet. One side gives off a more positive charge, one side gives off a more negative charge. And when you have that distribution, so you have this molecule that is bonded together, and it's not an equal distribution of the charges inside, that is what we call a polar molecule. Now, a polar molecule will act very differently from others. It actually describes a lot about how water behaves and works. If you think about water, if you've ever put ice cubes into a glass of water or a soda, usually when things freeze, they become more dense. So the colder they get, the more dense they become. That's not the case. Ice actually floats. And so that situation, that setup of being polar, is going to give it different properties than what we see with other things and how they behave. It actually gets some very unique characteristics. But understand that when we talk about a polar molecule, it is simply indicating that you have a negative side and you have a positive side. I want you guys to go ahead and jump down to where acids and bases are located. So the last thing that we need to talk about is pH. So when we talk about acids and bases and pH, when you think about water, water is H2O. And water is very basic. We drink it, we bathe in it, swim in it. And so we tend to not really think that it has anything that's too crazy going on. But when you look at the water, H2O, 2 hydrogen, 1 oxygen, when that water dissociates from itself, it actually is going to break apart, and one of the hydrogens are going to go off on their own, and the second hydrogen and the 1 oxygen molecule are going to, or oxygen is going to go off together. So hydrogen goes off, and then the other hydrogen and the oxygen, they go together and they stay together. What happens in that separation is the hydrogen that gets left by itself is actually going to carry a positive charge to it. The hydrogen and oxygen that separate and stay together, separate from the other hydrogen, are going to have a negative charge. So you get this separation, 1 hydrogen by itself carrying a positive charge, hydrogen, oxygen carrying a negative charge. That is actually the makeup of acids and bases. All of those hydrogens that result from the breaking of that water are going to form what you guys know as an acid. All of the OH negatives that go off together, they are going to form your bases. So when you think about some of the strongest acids and bases that can do tissue damage and burn through skin and things like that, they actually originate from H2O. Break it apart, and now you get the makeup for your acids and you get the makeup for your bases. So looking at acid and base concentration, we use the pH scale to actually measure how strong an acid or base is. And your pH scale is a range from 0 to 14. 0 is the lowest you can have on the pH scale, 14 is the highest, and 7 is what we call neutral, right in the middle. Now, the unique thing about the pH scale is usually you start at 0, and as you move away from 0, things get stronger. That is not how your pH scale works. Your pH scale technically starts at 7. And as you move from 7 and get closer to 0, that is the acid side of your pH scale, the acid gets stronger. From 0 down to 7, from 7 down to 0, the strength of the acid is going to intensify. On the other side, from 7 to 14, that is your base side. As you go from 7 and get closer to 14, the strength of your base is going to intensify. So the overall scale is from 0 to 14. 7 is neutral. No acidic properties, no basic properties. As you move away from 7 and get closer to 0 or closer to 14, the strength of the acid or the base is going to get stronger. Now, 14 doesn't sound like a huge number, but what you have to understand is that every time you move one number on the pH scale, you're actually increasing in intensity tenfold. So to go from 7 to 6, the strength of that acid increased 10 times. To go from 7 to 5, that's 100 times increase. Because from 7 to 6 was 10, from 6 to 5 would be another 10. 10 times 10 is 100. So as you move down that scale, every single number you move, it's 10 times the strength. Likewise, if you're moving toward 14. So on the pH scale, usually your acid side is going to be represented in red. Your base side is going to be represented in blue. People get caught up in the term base. Base is always safe to us. Ever played hide and seek or you played tag? Base was where you wanted to get, you were safe at base. That's not the case on the pH scale. A strong base can do just as much damage as a strong acid. So when you're looking at that pH scale that is in your packet, shows you pH of 0 all the way up to 14, shows you your neutral point. Okay. Anything, you have that diagonal line that is cutting through the middle, anything that is above that diagonal line, that is all going to be a measure of the H pluses that you have, those hydrogen ions. Anything that is below that diagonal is telling you how many hydroxides, those OH negatives, you have. So you'll notice that if you're looking below that diagonal line, at a pH of 0, you have very few hydroxides. And as you continue to make your way closer to 14, the number of hydroxides that you get is going to increase. The last slide that you guys have talks about your pH levels. Normal pH in a human should be 7.4. That is ideal. We are allowed a little bit of fluctuation from 7.35 to 7.45. Very small degree of fluctuation there. When you start getting below 7.35, things are not going to work how they should. If you get above 7.45, same thing is going to happen. The term that you would use when your pH is in the range of 7.5 to 7.8 would be alkalosis. So that comes from alkaline, which indicates base or basic. So if you think about where you would be on that pH scale, from 7.4 to 7.5, creeping up to 7.8, you are moving higher on that base side of the pH scale. On the other side, 7.3, making your way to 7.0, now we're moving closer to 0, so we're moving on the acid side. That is referred to as acidosis. So when you hear those terms, that's where they come from. Alkaline means you're moving on the base side. Acidosis indicates acid. That's the side of the pH scale that you are moving on. Now, I know a lot of information. Hopefully you have had some chemistry in your background to kind of draw off of. I am going to come back and we are going to talk about this in class. We are going to do representations on the board. You guys are going to work through some things and kind of put some visual to the material that we covered in our conversation tonight. So if you're still not 100% comfortable with it, that's perfectly fine. We will reinforce and go over things in class, and I will definitely take questions if you have them.